Hey guys, welcome to the 2012 Level 2 Waves exam. We're just gonna get straight into it. Okay, so question 1, curved mirrors and lenses. Sara observed that it is possible to get a virtual image of an object using either a concave or a convex mirror. On each of the diagrams below, use a ruler to draw the path of two rays of light from an object, draw as an arrow, to produce a virtual image for both a concave as well as a convex mirror. The vertical line represents the curved mirror. Okay, for the concave mirror, our mirror is going to be caving in, okay, it's going to look exactly like this, okay. So we're going to be drawing our object, okay, our object is going to be represented by an arrow simply facing upwards. That's just going to be our image. It's going to be our image here. Okay, there's our image, okay, we're going to draw our two rays, okay. Our two rays, one is going to be going directly perpendicular 90 degrees to the top of the arrow. Or not top of the arrow, but top of the object, okay, going to go perpendicular, okay, and it's going to reflect back towards the focal point, okay, so it's gonna hit the ray is gonna hit the mirror, and it's going to reflect back and towards the focal point, so it's gonna look something like this. Okay, so the wave will look something like this, okay, and just keep going down, okay. So another wave going to be drawn directly towards the horizontal axis, okay. So this ray is going to reflect back in this direction at exact same angle. So this is angle theta here, so this will also be angle theta, okay. So it's going to reflect directly even on both sides, okay. So we're gonna get an approximation here. I can't be perfect, I don't have a protractor with me, but it will look something like, should look something like this. Yeah, should look something like this. So both of these is angle theta. This is angle theta here, and this is angle theta here. Okay, so as you can see here, the rays actually don't touch, okay. So as you can see, ray A, so ray number A and ray B, they don't touch anywhere in the points, okay. So this means that the image produced isn't a real image. It's going to be what they call a virtual image, okay. So the rays in reality, they don't actually meet, okay. So as you can see in this image, these two rays, they don't meet, okay. They don't touch each other. So what we're gonna do right now, we're gonna get a dot back the arrow. Oh, that's terrible. What am I doing? We're gonna dot back the arrow. Okay, so is there an option here? We're gonna use a straight line to dot back our arrows. Okay, well, not arrows, but our rays. Okay, so if I kept dotting back ray A, okay, if I kept dotting it back, it would look something like this. It would just keep going, keep going, keep going. And if I dotted back if I dotted back ray number B, okay, it will go in the exact same direction, but not same direction. It'll go opposite direction. Okay, so we're just gonna keep extending the ray as if it was going backwards. So where the two rays meet, okay, so the two rays are now meeting. Okay, so if I extend the ray backwards, it's now meeting. Where these two rays meet is where our virtual image will be produced. Okay, so there is our enlarged virtual image. So our image will appear right here. So there we have our image. So we're gonna say this here is our object, and our image is here. So because the rays don't actually touch, because we dotted it back, okay. So what it would have looked like if we dotted it back, okay. So therefore, where these two rays meet, this is a virtual image. So image, it's virtual. But you can also see that the object here, the arrow is only this big. But the image created is it's almost twice the size, okay. So therefore, you can also say that the image is enlarged, okay. So it's an enlarged image, and it is upright, okay. It's still facing upwards. So this object is facing upwards, and the image is also facing upwards. So therefore, you can also say that the image is upright. Okay, we're gonna be move on to a dang it. Dang it, what did I just do? Oh, that's so annoying. Okay, hopefully, okay. So guys, sorry about that. My iBooks has been playing up really badly recently, so if you guys missed that, okay, just rewind back to the video, okay? I'm sorry about that. Everything just disappeared. Yeah, sorry about that, guys. So just rewind in the video if you need to see the diagram again. I apologize once again. So we have our convex mirror here, okay? Our convex mirror will be facing the exact opposite way. Our convex mirror should look exactly something like, it should look like this. Okay? So if we have our image, gosh. Okay, sorry, I need to refresh the app. Okay, oh, the image is back. Okay, sorry, the image is back. It's not playing up anymore. So hopefully this will allow me to get an arrow here. Okay, good. Sorry about that, guys. So once again, we have our image. Okay, we have our not image. We have our object. Okay, so this is our object. Okay, and once again, we're gonna draw our two rays. Okay, so one ray is gonna be exactly perpendicular. Okay, 90 degrees, and it's going to hit the mirror. So as you can see, this part here, okay, it's curving upwards, so it's going to hit the mirror and it's going to bounce in this direction. But if we dot it back, it should be hitting the focal point. Okay, so we need to redraw the focal point on the other side. Okay, so just need to measure out the focal point and we redraw on the other side. So it should be something. Should be like somewhere here. I know it's not very accurate. In the exam, you'll need to use a ruler to measure it out. In the exam, you'll have a ruler, but I don't have a ruler with me right now, so it makes it a bit harder for me. So, okay. So we have our focal point on both sides. Okay, so the ray is going to bounce back towards this end here. Okay, it's going to reflect back. But it's going to, if we dot back the ray, it's going to pass through the focal point. So it should look something like this. Should be going right through the focal point. Once again, the other ray, okay, is going directly below to the horizontal axis, and it works the same way as the concave mirror would. Okay, so the ray is gonna go back to the horizontal axis, and then it's going to reflect so that both angle theta is equal. Okay, so both of this angle theta here, this angle theta this angle theta is equal. Okay, so just get approximation here. Okay. So as you can see, once again, the rays don't actually touch. So we have our ray A this time is here, and our ray B this time is here. As you can see, these rays aren't actually touching. So once again, the image produced, it's not a virtual. It's not a real image. It's a virtual image. Okay. So so it's basically it doesn't actually exist. So it's virtual. Okay. So in order to find out where our image is, we're going to be dotting back the rays. Okay, so I'm going to dot back ray number B to where it hits the ray number A. So as you can see, the point of intersection is here. So that means our image will be produced at the point of intersection. Okay, so our image will simply be produced at the point of intersection, and dotting it back down to the horizontal axis. So it should look something. Okay, so it's not very straight. Okay, so our image. Okay, so our image would be here. Okay, so once again, our image doesn't actually exist. So because the rays don't actually touch each other in Okay, so in reality, the rays will hit the mirror. So hit the mirror here, and it'll just bounce back in the direction that is dotting back to a focal point. And ray number B will hit the horizontal axis and dot back where both angle thetas are equal. So in reality, the rays don't actually touch, but the image will be produced at the point where the rays would have touched if I could extend it backwards. Okay, so as you can see, our image here. Okay, so it's virtual virtual, okay, it's upright once again. And this time, okay, the image is smaller than the object, so we're gonna say that the image is diminished. So it was smaller than it once was, okay? Alright, describe two characteristics of virtual images in mirrors, okay? So the two characteristics, okay, number one, okay, the rays never actually touch. The rays never actually touch. Oh, wow. Never actually touch. And number two, okay, so if I were to broadcast this image onto a screen, so for example, like in class, for example, we have a projector. If I were to broadcast this object onto a projector, it wouldn't show up, okay? So it would not show up on a screen or projector. And the reason for that is because it doesn't actually exist. Only real images can be projected onto the projector and screens, okay? Okay. Alright, next question. Sara places a candle at a distance of 4.5 centimeters in front of the convex mirror. She uses a candle that is 2 centimeters high as the object. The focal length of the convex mirror is 6 centimeters. Calculate the height of the image formed by the convex mirror. Okay, so we what did they give us? Okay, they give us a distance, the distance of the candle in front of the convex mirror. So the candle is 4.5 centimeters away from the mirror. Okay, so therefore we're gonna say that the distance or object is 4.5 centimeters away from the convex mirror. So therefore our distance of object, okay, so our DO, distance of object, equals to 4.5 centimeters. We also know that the candle is 2 centimeters high, okay, so our height of the object, which is HO, is equal to 2 centimeters. The focal length of the convex mirror is 6 centimeters, okay? Okay, so just remember, in a convex mirror, we will always use the focal length as a negative number, okay? So our focal length is not 6, but it's negative 6, okay? So our focal length is equal to negative 6 centimeters. So what is the height of the image formed by the convex mirror? So we don't know our HI, height of image, we don't know. Okay, so the first thing we're going to be able to do in these questions, the first thing we're going to be doing is finding the distance of the image. Okay, so how far away from the mirror is the image? We do that by saying that 1 over f is equal to 1 over do plus 1 over di. Okay, so 1 over negative 6 is equal to 1 over 4.5 plus 1 over di. Okay, so we don't know our distance from image. Okay, so in order to do this, we'll be using a calculator. So we're gonna say that 1 over negative 6, so 1 over negative 6 minus 1 over 4.5, and then we're going to be doing 1 divided by our result to get our di. So 1 divided by our answer will give us our di. So our di comes out to be 2.57 centimeters, negative 2.57 centimeters. Okay, to answer your question on why the focal length is negative, okay, think about it this way. We have our convex mirror here, okay, and as you can see the image, so if this is the mirror, so this vertical axis here is the mirror. So we have our mirror here, and our image is actually formed behind the mirror, okay? So because our object is measured from the mirror to our object to the mirror is our DO, so our distance of object. But as you can see, our image is formed behind the mirror. So therefore, our distance of the image will therefore have to be a negative number. Okay, so note if we use the focal length as positive. Let's pretend we say that focal length is positive. If we get focal length is positive, okay, then you'll actually get the incorrect answer, okay? So it's important that you always remember that in a convex mirror that the focal length is negative. And you also have to remember that in a concave lens, the focal length is negative, okay? So convex mirror and concave lens, okay? And the convex lens is positive focal length, and the concave mirror is a positive, okay? It's positive focal length. So you have our DI equals to negative 2.57 centimeters, okay? Now we're going to be using that DI over DO is equal to HI over HO. Now we have our DI and DO, and we also have our HO. So it's really easy to be able to find our HI here, okay? So basically, negative 2.57 divided by DO, which is 4.5, is equal to HI, we don't know, divided by 2, which is our HO, so 2 centimeters here. Now we're going to cross multiply, okay? So we're going to say that 2 times of negative 2.57 is equal to 4.5 of HI. Okay, if we plug this into our calculator, we should be getting that 2 times of negative 2.57, that equals to negative 5.4 divided by 4.5 will give us our height of the image. The height of the image comes out to be, sorry, I just need to calculate it. Comes out to be 1.14 centimeters, okay? So our HI should come out to be 1.14 centimeters, okay? So getting all the way to HI equals to 1.14 centimeters gets you an excellence grade. To get a merit grade, you're looking at getting the DI correct, which is negative 2.57 centimeters. That'll get you a merit. To get your excellence, to get your achieved grade, you're looking at using the positive focal length and getting that HI equals to 8 centimeters, okay? So consistent use of focal length is 6 centimeters, okay? That will get you an achieved, okay? So achieved is also possible. Okay, I'm going to go over the grading for these last two questions. I totally forgot. So 1AII, so enlarged virtual image produced, that will get you a merit grade here. So enlarged correct ray diagram. okay. I will only get you an achieved grade, okay, to get the correct diminished diagram. For B, okay, so for B, to get a merit, okay, you're getting 2 correct points to get you a merit. Only 1 point will get you an achieved. So merit for both, achieved for only 1, okay. Alright, moving along. Jack is given 2 convex lenses. The lenses are identical in shape but have different refractive indices. Jack places the 2 lenses in the same distance from a candle and sees a virtual image of the candle in each lens. Explain why the images formed by the 2 lenses are different in size. Draw diagrams to help with your explanation. The arrow represents the candle. Okay, so basically, if we have a lower refractive index, that means the medium is less dense. And if you have a higher refractive index, that means the medium is more dense, okay? So for example, we have an object moving from air, okay? So this is a light moving from air. It's going to hit the mirror, which is made out of glass, okay? But for one, it's a lower refractive index, and for one, it's a higher refractive index. So one is less dense and one is more dense. So let's imagine it's hitting the less dense, which is the less dense glass, okay? Because it's hitting the less dense glass, that means that the light actually that the light rays actually slow down less. Because if we move it into the more dense, it will slow down much more because it's more dense, and therefore the rays will slow down a lot more. So therefore, there's less change in V for the less dense mirror. Okay, so because there's a less change in V, that means there's less bending of the ray. And because there's less bending of the ray, that means the ray will not bend as much, okay? So the ray is going to move, okay, it's going to move to here, okay? It's going to hit the mirror, okay? It's going to refract. Okay, it's going to refract downwards, okay, and it's going to hit the focal point here, okay? Okay, so for a lower refractive index, okay, the rays bend less, okay, so therefore the focal length is further along. However, if we have a higher refractive index, the rays are going to slow down more, and therefore when it comes out of the air, it's going to bend a lot more, so therefore our focal length will be a lot smaller. Okay? So that means, so the high refractive index basically represents that the light waves will be bending more, and because it bends more, it travels to the axis a lot sooner, and because it travels to the axis a lot sooner, that means the focal point must be a lot less, okay? So how does a lower focal point affect our what is it? Different sized candles? How does that affect the image produced? So how would that affect? So basically, if we have a lower focal point, okay, so basically, okay, we have our okay, so we have our equation. Okay, so our equation is 1 over f equals to 1 over do plus 1 over di. Let's say our focal length has gone down, okay? So our focal length has gone down, but our do remains constant, okay? So that means, okay, that means we have 1 over 1f, which is a lower focal point, minus 1 over do, which is a constant, and that equals to 1 over di, okay? So think of it this way. So we have our 1 over f, okay? So if we decrease the f, okay, so what's 1 divided by a lower number? Okay, it's greater, okay? So if we have a greater, so 1 over f, okay, so this result will be greater, and minus 1 over do, that's constant, so therefore this entire result will be higher, okay? So therefore, because this entire result is equal to 1 over di, 1 divided by a higher number will give us our lower distance distance of image, okay? Okay, so this will actually be lower, okay, and this will be the same, okay? So we know magnification, okay, that equals to di over do. Because we have a lower di, so our di has gone down, but our do has stayed constant. That means our magnification will also go down. Okay, that means with the length of the lower refractive index, that means that because the rays bend less, that means the magnification also decreases. Okay. However, it's the exact opposite of a high refractive index. We have our 1 over f equals to 1 over do plus 1 over di. So if we have a higher focal point, then this result here, what's 1 divided by a greater number will give us a smaller result. So this entire result will go down, minus 1 over do, which is constant, okay? Our distance of object we assume is constant. So therefore, this entire result has gone down, and that equals to 1 over di. Because we get di, okay, so how do we calculate di? So di is basically just 1 divided by whatever result we get here. So 1 divided by a lower number. So for example, 1 divided by 1 is 1, but 1 divided by 0.5 is 2, okay? So if we divide 1 by a lower number, we get a higher di. And then we have our magnification equals to di over do, okay? So our di has gone up, but our do has stayed constant, okay? So therefore, our magnification will also have gone up, okay? So therefore, okay, because our magnification is higher for the lens with higher refractive index, that means that our image produced will be greater when using a convex lens with a higher refractive index. Sorry. So how are we going to explain all of this in the word form, okay? So it's important to be able, it's good to understand, but it's also necessary to be able to explain. Sorry, this doesn't, okay. So how are we going to explain, okay? So, when rays travel from the No, actually, we're not going to start from that. Because we're going to say the light rays bend less when traveling in the lower refractive index, and this means that it will take longer to get to the axis and hence a higher focal point. Rays bend more in high refractive index, and hence the focal length is smaller. Okay, since 1 over f equals to 1 over do plus 1 over di. If we have a continue at the back. So if we have a lower focal point, then 1 divided by f will generate a higher output. Because we assume do is constant. Because we assume 1 over do is the same, then since di 1 over di since 1 over di equals to 1 over do plus 1 over f 1 over f minus that 1 over f minus 1 over do, so 1 over f minus 1 over do. Because 1 over f is a higher output, then the 1 over f minus 1 over do gives a higher output. To get di, we do 1 divided by 1 over f minus 1 over do, and 1 divided by a higher 1 divided by a higher number gives a smaller gives us a smaller di. Okay, so our di we have established is smaller. Okay, so we're going to say since magnification equals to di over do, our di has gone smaller. Di is smaller while do is the same. Hence, m is smaller. Hence lower refractive index gives a smaller image because the magnification is less. Okay, so hence the lower refractive gives a smaller image, and higher refractive index gives a bigger image. Okay, so getting all the way up to so you establish that since the rays will bend more so you can do it either way. Okay, so if we can say that the rays bend less in the lower refractive index and therefore the focal length is longer. And then you establish focal length and how the focal length affects the size of the image, and establishing that back to the magnification. If you're able to do that, then you'll get your excellence grade, okay? So you have to state that so basically your final concluding statement would be higher refractive index gives us a larger image. To get a merit grade, okay, to get a merit grade, you're only saying that the diagram for the lens of high refractive index shows a shorter focal length, hence the image is formed further away. So you're not linking it with the equations, okay? You're just saying that high refractive index, therefore further away. So just linking these 2 points together. To get an achieved, you're looking that the focal length is shorter, shorter for the greater refractive index, or you can say that the greater refractive index rays will bend more. So any of those 2 points will get you an achieve. So merit and achieve is both. All grades are possible for this question. Alright. Thank you for watching question 1 for the 2012 exam. Okay. I'll see you in the next question, which should be coming out very shortly. Thanks for watching.